Hey everyone, and welcome back to Frank's World of AI. I'm Alex Thomas, and wow, Stella, the advancements we're seeing in large language models just keep blowing my mind, honestly.
Totally, Alex. It's wild, right? And today, I really want to dig into something that's super crucial, but maybe not always in the spotlight: post-training methods. Like, how do we take these incredibly powerful pre-trained models and actually make them, well, useful? You know what I mean?
Yeah, absolutely. It's almost like they start as these brilliant general purpose minds, but then you need to teach them manners or a specific job. So when we talk about pre-training, what exactly are we referring to there? Just to set the stage for everyone listening.
Right. So think of pre-training as the model's childhood, if you will. It starts as like a blank neural canvas. And then it's fed this massive amount of text data, billions of examples, to learn language itself. Grammar, context, general world knowledge. It's basically trying to predict the next word in a sentence over and over until it gets really good at forming coherent patterns and understanding semantic links. It builds this incredible linguistic capability, but it's still, just a language guru, not necessarily a taskmaster.
Okay, so it understands language, but it doesn't necessarily know how to do things with that language, right? That's where post-training steps in?
Precisely. Post-training is where we teach it to, like, follow instructions, answer questions, reason through problems, even align with safety guidelines or specific brand requirements. It's all about transforming that broad linguistic foundation into something incredibly useful, safe, and often domain-specific for real-world applications. So, diving a bit deeper, one of the most fundamental post-training methods, and probably one people hear about most, is supervised fine-tuning, or SFT. It's pretty straightforward, really.
SFT. Okay. So what's the core idea behind it? Is it like giving it specific examples and saying do it this way?
Exactly. The goal is simple. You give it an input sequence, and you train the model to produce a very specific corresponding output sequence. So if the input is, "What is the capital of France?" you train it to output, "The capital is Paris." It's still using that next token prediction, but this time the input is kind of a condition, and the output is the sequence we want it to learn to generate. It really hones its ability to give us the right answer.
That makes sense. But what about real conversations, like with multiple turns back and forth? How does it differentiate between what I say and what it should respond with?
That's a fantastic question, Alex, and it's where messages formatted data comes in, what we often call instruction tuning or multi-turn chat tuning. Each message in a conversation is like tagged by role: user, assistant, system. This helps the model understand who said what. Under the hood, they're represented by special tokens that mark message boundaries. This prevents the model from, getting confused and thinking it's the user or something. There are even chat templates that translate our natural prompts into this structured, tokenized format, so the model understands its role.
Wow, so it's not just learning to answer, it's learning to have a conversation. That's a pretty big leap from just predicting the next word. So, Stella, once a model's been fine-tuned, what happens when new information comes along? Say, new financial data annually or evolving company documentation. Do you just fine-tune it again and hope for the best?
That's where continual learning becomes super important, Alex. And it's trickier than you'd think. The big challenge is something called catastrophic forgetting. If you just fine-tune it again, you risk overriding older, valuable knowledge. It's like teaching someone a new skill, but they totally forget their previous skills in the process, which is obviously not ideal.
Catastrophic forgetting. That sounds, well, catastrophic. So, how do researchers tackle that? Is there a way to, update the model without losing all its previous training?
Thankfully, yes. One really promising solution is orthogonal subspace fine-tuning, or OSFT. What it does is it actually targets the least important model weights for updating. It tries to figure out which parameters contribute the least to previous tasks and general model performance, and then it focuses updates there. This minimizes forgetting while still allowing the model to learn new information. It's really clever, honestly.
So it's selectively updating rather than just a blanket overwrite. That's incredibly efficient. How does it decide which parts are least important?
It uses something called adaptive singular value decomposition, or SVD, to break down each weight matrix. High-rank components with large singular values capture critical information, while low-rank ones are less significant. OSFT then uses an unfreeze rank ratio to decide how much of the model remains trainable. You can set it from 0, meaning everything's frozen, to 1, which is full fine-tuning. Most use cases strike a balance, like zero point 0.5, to learn new stuff while protecting existing knowledge. It gives you really fine-grained control over that trade-off. Now, speaking of efficiency, we absolutely have to talk about parameter-efficient fine-tuning, or PEFT. This is fantastic for reducing memory and compute costs, especially when the base model already has a ton of knowledge, and you just need some minor tweaks.
PEFT. So it's about making smaller, smarter adjustments instead of retraining the whole giant thing?
Exactly. You're only modifying a small subset of parameters or adding lightweight trainable components. The simplest form is prompt tuning. Instead of changing the model's core weights, you just learn a small set of soft prompt vectors that get prepended to every input. These vectors act like a trainable instruction, guiding the model without actually altering its internal representations. It's like whispering a suggestion to the model rather than rewriting its brain, you know?
Oh, that's super interesting. So the model itself isn't changing, but its interpretation of the input is being nudged. What about something a bit more substantial than just a prompt?
Well, then you've got low rank adaptation, or LoRA, which is super popular right now. LoRA injects small, trainable matrices directly into existing model layers. These matrices approximate the weight updates that would happen during full fine-tuning, but they use a tiny fraction of the parameters. It breaks down a big weight update into two much smaller matrices, significantly reducing computational complexity. It's incredibly efficient. Often, you get comparable performance to full fine-tuning with way less data and hardware. And there are extensions too, like QLoRa for even less memory usage and OLoRa for a better initialization stability. It's a game changer for accessibility.
That's truly amazing how they're finding ways to refine these models without needing to rebuild them from scratch every time. So what about reinforcement learning? I've heard that mentioned a lot in the context of LLMs lately.
Oh, reinforcement learning, or RL, is another huge branch, and it's fascinating because models improve through iterative feedback rather than just static labels. Think of it like a game. An agent, that's our model, interacts with an environment, takes actions, gets rewards, and observes new states. The rewards tell it how desirable an output was, and it uses that to refine its reasoning and improve its factual accuracy over time.
So, teaching a model to play chess almost? It makes a move, gets feedback on how good it was, and then learns to make better moves?
Exactly. In the context of language models, the actions are generated token sequences, and the inputs are like the state. A practical way to implement this is through rules-based verifiers. These are deterministic evaluators that automatically check if a model's response meets objective criteria. Like for a math problem, it's a 1 if correct, 0 if not. This provides scalable, automatic reward assignment, which really speeds up learning cycles, and it helps models understand which reasoning patterns lead to better outcomes.
That's super clever. So it's not just guessing, it's actively learning from its own attempts. Are there specific RL approaches that are really popular for LLMs right now?
Oh, definitely. Group Relative Policy Optimization, or GRPO, is a big one for language and reasoning models. GRPO samples multiple rollouts, different solution paths the model might take for a single prompt. A rules-based verifier then evaluates each rollout, assigns rewards, and those rewards are normalized to figure out how strongly the model should prefer certain reasoning paths. This helps improve both stability and correctness while keeping the model's expressive capacity. There's also direct preference optimization, DPO, and reinforcement learning from human feedback, RLHF, which are super important for aligning models with human preferences interactively. And beyond all these incredible techniques, post-training is also touching on other really exciting areas. Things like model merging, where you blend weights from multiple fine-tuned models to combine their capabilities. It's like creating a supermodel from several specialized ones.
Model merging? That sounds like something out of science fiction, actually. Combining different expertises into one brain? What else is on the horizon?
We're also seeing a lot of work in post-training compression, which includes things like quantization and sparsification. These methods reduce model size while trying to keep accuracy high, which is crucial for deployment, right? And then there's inference optimization, focusing on making models faster and more efficient when they're actually serving users. So it's a whole life cycle: pre-training for mastery, post-training for specialization, and then inference for efficient deployment. It's truly a complete picture.
That's a lot of ground, Stella. For our listeners who are keen to try some of this out, where can they even begin to experiment with these advanced algorithms?
That's the best part. Developers can actually jump right in with the open source Training Hub. It's an abstraction layer that gives unified access to all these modern post-training methods. It has a really consistent Python interface, supporting multiple community backend implementations. You can find it on GitHub, install it from PyPy, and it already supports SFT and OSFT. They're planning to add reinforcement learning and PEFT methods like LoRA by the end of 2025, too. It makes all this stuff super accessible. You just call a Python function for SFT or OSFT, define your model and data paths, and you're good to go. It handles all the heavy lifting. It's really simplifying a complex process for developers, which is fantastic.
That sounds incredibly powerful, making these sophisticated tools available to a broader community. Stella, this has been an incredibly insightful deep dive into LLM post-training methods. Thank you so much for breaking it all down for us.
My pleasure, Alex. It's such an exciting field to be in.
And thank you all for tuning in to Frank's World of AI. If you enjoyed this episode, please like, share, and subscribe. And make sure to visit franksworld.com to stay on top of the latest in AI news and research.